An incredibly far-away, intelligent civilization dumping heavy, unnatural elements into their host star to gain the attention of other intelligent life forms in the universe, such as us humans. While in my opinion, this suggestion is an absurdly unlikely hypothesis to the extent that we might as well discard it, there is definitely something strange occurring at a star known as Przybylski's star. And this fascinates me as a geologist. While geological processes move and concentrate various elements on Earth, it is also important to understand how these elements came to find themselves on Earth in the first place. And, for all intents and purposes, we know how the 80 stable elements such as gold, silver, and lithium ended up on Earth. Elements starting at number 41, niobium, originated only through dying low-mass stars, Type 2 supernova, or one of the most energetic events in the modern universe, the collision of two neutron stars. Neutron star mergers known as kilonovas are responsible for creating the vast majority of elements which do not have a single stable isotope, in other words, are radioactive. This includes thorium, radium, and even per a scientific paper, perhaps even element 98, californium. Everything higher on the periodic table has never had a confirmed observation anywhere in the universe, at least naturally, except by us humans creating them as the result of nuclear weapons or in a lab. Hence why the periodic table currently only goes up to element 118, oganesson, which was first synthesized in 2002. Yet, since then, scientists have been largely at a roadblock while trying to create even higher numbered elements due to current methods making creating them an absurdly difficult, time-consuming, and costly process. It doesn't help that the longest half-life, or time it takes for an average of half of a sample of an isotope to undergo radioactive decay, for every single isotope known of the three highest numbered elements is 0.057 seconds. Even higher numbered elements, if they do exist naturally, are expected to have even shorter half-lives than this, so you might be surprised to learn that one hypothesis to explain Przybylski's star suggests that it has a relative abundance of an element not yet discovered by science, specifically element 126, unbihaxium. Before I continue, I would like to thank this video's sponsor, RadiaCode, which has become a repeat sponsor of my work. RadiaCode is a company which produces affordable yet highly effective smart and portable Geiger counters and spectrometers. These devices not only show you the level of radioactivity an area or object is producing, but also shows you what specific isotopes are creating said radiation. For example, I recently brought my RadiaCode 110 device shown here to the quartzite and Tucson Gem and Mineral shows. At Tucson, the device picked up radioactivity from hard-to-spot tiny splotches of carnotite on select pieces of petrified wood that vendors were selling that they did not know about. Meanwhile, at quartzite, I spotted something even more interesting. I detected a highly radioactive person, which caused my RadiaCode device to register a jump from 15 to 1800 counts per second. The culprit, as you can see here, it was quickly identified as technetium-99m, the main isotope used in nuclear medicine. RadiaCode devices let you visualize the energy lines of incoming gamma rays and explore natural sources, allowing you to see if a worksite, house, rock specimen, or ore deposit you happen to be mapping is radioactive, and there is even a mapping feature you can use as part of a free mobile app paired with a device. And now is the perfect time to buy, as if you use this link shown on the screen in the top right or in the video description, it will apply an automatic 5% discount to any order you make. Now back to the video. And if unbihaxium does exist in this star, so do concentrations of elements 119 through 125, meaning it has 8 elements not yet confirmed by science. Before I explain why this has been suggested, I want to elaborate and explain what makes Przybylski's star so strange. Located 356 light-years away, it should, for all intents and purposes, not contain any elements higher than bismuth and be rare earth element rich in iron poor, representing a typical AP star. Yet, while the latter 2 points do describe Przybylski's star, it strangely has many elements heavier than bismuth, specifically actinides. Actinides are universally radioactive elements that eventually decay into more stable elements such as lead. At Przybylski's star, even up to element 99, Einsteinium had a confirmed detection, which for reference has a half-life at its longest of 471.7 days. For all intents and purposes, these elements shouldn't be present here. They should have already decayed into something more stable, unless there was an abundance of an even heavier element simply decaying into the observed actinides, thus replenishing what would otherwise have decayed into lower-numbered elements. And if those super heavy elements exist at their implied abundances, regardless of possible explanation, it likely means the existence of element 126 within the star. Now, it is fully possible that there is a hard limit on how high of an element can form naturally within a main sequence star that is lower than 126 but higher than 98, but I deem this to be less likely. In the periodic table, there are a series of elements that have the capability of having longer half-lives than their peers right below and above them, due to one of their particular isotopes having a specific number of protons and neutrons. These magic numbers that strengthen a radioactive isotope against decay occur when a full shell exists in an isotope. And if both the protons and neutrons in an isotope contain these magic numbers, an isotope is doubly magic, leading to an exceptional relative stability. Above element 99, the next isotope that could theoretically exist, which fits the doubly magic specifications, is an isotope with 126 protons and 184 neutrons. In other words, an isotope of element 126, unbihexium. No one truly knows how long a half-life would be for unbihexium 354, but current models suggest an exceptionally long period considering how high of an element it is, possibly on the order of a 10 to 100 year half-life. If this is correct, then any naturally occurring detection of an element above 98 could be thought to be a decay product from element 126 doubly magic isotope, which means it might contain every single radioactive element in some abundance below it, including 7 additional undiscovered elements. This is of course a huge if, an extreme one in fact, and when dealing with theoretical astrophysics, it can be tough to prove anything. Current hypotheses to explain why such heavy elements exist in the star include 1. That Przybylski's star has an unseen closely orbiting neutron star which is bombarding the larger diameter star with intense radiation and material so that it can trigger the rapid neutron capture process. However, the problem here is that there is no evidence that Przybylski's star has a companion star. 2. That a large chunk of neutronium from a neutron star somehow ended up being absorbed by Przybylski's star, perhaps ejected by some very distant and ancient supernova, causing the R process to occur within it. 3. That the unusual composition of Przybylski's star is triggering some process so far unknown to science, which is more common than we might think, and can actually create higher numbered elements than Einsteinium. Or 4. That some intelligent alien life is intentionally salting the star to gain the attention of other intelligent life forms in the universe. However, the explanation for astronomical phenomena has yet to ever be aliens or alien life, therefore I think the suggestion should be discarded. In discussing the R process, which for reference occurs more than 100 times per second per atom when it does occur, element 98 isn't truly a hard cap on how high of an element that can be created by this method in highly energetic events. Rather, it more so represents the current limit of our science's ability to detect such elements, especially given that detecting spectra from elements with absurdly short half-lives is insanely difficult. The sad thing is, even if elements 119 through 126 do indeed exist in Przybylski's star, their hypothetical confirmation would not be classified as discovering multiple new elements, as it is absolutely essential for an element to be directly observed in the lab and not light years away to meet the classification as a new element discovery. Regardless, if these elements do exist there, figuring out how they came into existence might give scientists a new method for creating ultra-high-numbered radioactive elements in a lab setting. Besides, per one source, while there are currently 118 chemical elements known to science, in theory it should be possible for elements as high as element number 137 to one day be created. However, there is a fifth explanation. It is quite possible that our data gathering methods are wrong and that no actinides actually exist in Przybylski's star. A special thanks once again to RadiaCode for sponsoring this video. And a special thanks to my patrons and YouTube channel members for supporting my work.